If a sequence is given by a functional prescript, so you have a formula for the sequence, then many times you can use limit rules in order to calculate or even decide upon convergence of a sequence, or you can calculate the limit of a sequence. This is not always possible. Sometimes you need just a couple of properties that you can show for a sequence in order to be able to state that it converges. And if you know it converges, then maybe you can calculate the limit. So here the general topic is, the topic of today is monotonic convergence of a sequence. Well, first we need to make sure that we understand what is a monotonic sequence. Well, first we're going to look at monotonically increasing sequences. So when is a sequence monotonically increasing? Well, its subsequent elements are going up. So if we have an plus 1, which has a larger index than an, then an plus 1 should also be larger or equal than an. In that case, we call the sequence monotonically increasing if this also holds for all indices n. Similarly, we can call the sequence an monotonically decreasing. Yeah, and you can guess what happens if the reverse inequality holds, right? So if a1 is larger than a2, a2 is larger equal a3, a3 is larger equal a4, etc., etc. And we call the sequence just monotonic if one of these properties holds true, right? So if one of the above statements holds, so either the sequence is monotonically increasing or it is monotonically decreasing. So if we would have a sequence with elements 1, 4, and then 3, then this is neither monotonically increasing, neither nor monotonically decreasing, so it's not monotonic. Okay, let's discuss some examples. So the first example, let's continue with a very easy example we also discussed convergence with. It's 1 over n. an equals 1 over n. Yeah, so this sequence is monotonic, and we know that we start with 1 and then a half and then 1/3. So we see that this sequence is decreasing. So this is monotonically decreasing, right? It's easily proven algebraically, but we won't do it here. Another sequence, Bn, is the exponential e to the power n. This sequence is monotonically increasing. Yeah, e to the power 1 is smaller equal than e to the power 2 is smaller equal e to the power 3, and so forth. Okay, now a sequence which is defined by minus 1 to the power n over n. So if we look at elements of this sequence, then what we get is, first we get minus 1. Yeah, just minus 1 to the power 1 is minus 1, divided by 1 is minus 1. And if we plug in 2, then we get minus 1 to the power 2. So the sign is positive again. Minus 1 to the power n gives just the sign of this expression times 1 over n. So then we get a half. And the third term in this sequence is minus 1 over 3. So here you see a pattern that from minus 1 to a half, you see an increase, and afterwards you see a decrease. So this sequence is not it's not monotonic. It's alternating in signs, so it cannot be monotonic. Another property that turns out to be ultimately useful is the notion of a bounded sequence. Well, when is a sequence called bounded? Well, an is bounded if if the elements in the sequence cannot get arbitrarily large or arbitrarily small. This means that they are contained inside some interval. All the values are contained in some fixed bounded interval, and this is equivalent to expressing that there exists a constant m larger than 0 such that all the elements are contained, all elements an are contained in minus m as an interval. Yeah, this means that in absolute value, we see that an is smaller or equal than this constant m, and this should hold for all the index numbers we have. Okay, so let's see in the previous examples which of the sequences we've seen are bounded. So here, let's see, the first example we had was an equals 1 over n. Well, this sequence starts with 1. The second element is a half, 1/3, etc. So we see that all the elements are covered by the interval 0, 1. So here we could take m is bounded by prescribing the value m equals 1. All the elements are in absolute value. Well, all these elements are positive. So all these elements in absolute value are smaller equal than 1. So an upper bound is m equals 1. So now we have this sequence, right? So the exponential sequence with e to the power n. Well, this sequence is unbounded, right? Since we cannot bind, we know that the exponential function for n to infinity, we see that e to the power n goes to infinity. So we cannot bind this, prescribe a bound for this sequence. So no such m exists. Yeah, and I invite you to show this formally. Now the other sequence we had, was this alternating sequence, minus 1 to the power n divided by n. And give it a thought. Well, it was not converging, right? So, or it was not, it is converging, but it's not monotonic, but it is bounded, right? So if you take the absolute value of Cn, right? So if you take the absolute value of Cn, you just get the first sequence, right? So that would be An. And An is bounded, so Cn is also bounded, since the absolute value of Cn is always smaller equal than m. So we can take as an upper bound for this sequence m equals 1.